Now, could you just respond? You can hear me. Sound now? Okay. I think there's a problem with my handphone. When I plug in the headphone, then the sound doesn't get transmitted. Okay, so we are going to go to our lecture today, learning. So today's a new sort of like not new topic, but a topic that is very similar to the one that is in previous case, in the previous lecture that we have done. Okay, for those who come in late, I'll let you to do the attendance later. Okay, so okay, so, the lecture we're going to talk about today is part 6.1. So you can click on part 6.1, then you would be able to launch the notes that I just updated yesterday. So this is my 6.1. My screen is always screen get blocked by the WebEx. So today we're going to talk about this topic on solving these square problems. Okay, so it's already 3:10 now. A bit late, but doesn't matter. Okay. Now today is like this. We're going to learn what the things that we have did in the previous class. Now, in the previous learned, let me point to the previous class. So the previous class is about the F-solve. So I'll make some revisions on F-solve thing first. Where am I? Okay. Now, when we talk about part 6, what we are doing is like, so I give you some function and you minimize it. So that was basically the situations. Okay. So in the previous case, when we use F-solve, what I do is that I give you two equations, and then you try to find me the solutions. Other than that, the F-solve also allows to do what you call the fitting. I think fitting is not in chapter 6, in lecture 6, but I think it is in part 5. So let me go to part 5 instead. I want to show you part 5. I cannot be shown on screens. Yeah. Many people in. 5, part 5. Maybe I call my part 5 from here is better. So the part 5, we use the FSOLVE to do what we call okay, my part 5, I just want to refer to this. The part 5 has these functions, right? So for example, you have done your tutorial. One of the tutorials is I give you some data point, and then I ask you to fit the data point onto some functions. So you have this data point that is given to you, then you are given some functions. So what is the best fit parameter for the function such that the functions would go through all the data points? So the optimal the values of the fit parameter so that you can get all the points to be gone through by the functions. So that is what you did today. Okay. Now look at the screen that you see here. I'm giving you some data point, right? So these are like random data point, but it's actually not random. It looks like a sinusoidal function, right? So there are many data points, and when you look at can be so this function is called y equals to a sine. Now let me make it larger so you can see it better. So it looks like this data point, where each of these data point has xi, yi. So if I give you this data, then and I ask you to find a function that should go through smoothly all these data points. What should you do? First, you have to of the form of the function that could be best used to. So you should first think of what is the function that could go to this point. So you have to choose the correct form of the function. So in this case, if you it looks like a sinusoidal function. So you will think, okay, fine. You would want to use a sinusoidal function to fit all the data points. So in this case, we choose a model. So in this case, a model is just a different name for a function that you choose that could go through all these data points. So in this case, the example that you see on the screen, the model in the form of a sine pi over t x plus theta. So this is like a sinusoidal function, but in this model, you have a few parameters. So the set of parameters are a, theta, that is shown on the screen. So this is a set of parameters function. So in this example, you have this data point xi, y. Then you also have to find a model that could fit this data. So when you talk about model, you're talking about a formula. And in this formula, it has some three parameters. So in this example, the parameters is a and theta. So in general, we would use this equation y equals to f with a bracket p, comma xi to describe the functions. So bracket px is what we call the model to be fitted. Okay, so in this model, the values of a, theta, and t are the three parameters in the model that is not known. If you can find what are these numbers for the parameters, then using these parameters, you'll be able to plot the functions of the model. And if these numbers a, t, and theta is correct, then the function should go through all these points nicely and beautifully. In this sense, this is an optimization problem. So in principle, you can use the FSOLVE in the previous lecture to get you the best value for t and theta. But sometimes FSOF doesn't work very well. So in that case, we have to find a better way to obtain the parameters in the model. So the whole exercise is what we call model fitting. You are given a set of you are given a set of data x and y. Then asked to find the best fit parameters for your model. So if your best fit parameters are found correctly, then when you put these numbers back to the model should produce a line that should fit through all these data points the best manner. Okay, so we are going to see how we do that. Okay, we're going to see how we can use these functions in Python that can allow us to find the best fit. Now, before we proceed on, I just want to let you know the principle of how this optimization works. So the optimization in this sense that is so like you can read it here. We seek the values of this parameter that best fit the data points by the model. This is an optimization problem in the sense that we wish to know what are the values of this parameter for which the sum of all residue is minimum. Now, what is this? This I think I have mentioned this some times ago. So in order to find the best fit parameter, or P, what you need to do is try to adjust the values of the parameters. In this case, you have three parameters, and theta, so that which is called R square is a minimum. Now, what is this R square? The R square is the sum of what we call the discrepancy. Now, I think I have a graph here, if I'm not mistaken. Let me check it out. I run this thing. Start and click or run off. Yeah. Okay. So you can go into the lecture notes. So in the lecture notes, you should be able to see this. Okay, this is an example of what we call and well, say for example, you have many data. This is X. These are all the data points X and Y, and the red color is what we call the model that you need to fit. And you do not know what are these three parameters P. So you just simply assign some values to the parameter, then you'll be able to get a continuous function y equals to f. Then you, for example, you look at this particular point, xi, yi, and then when x equals to xi, values of the function on this smooth curve is given by y. So y is the functions, is the values of the function y equals to f evaluated at xi. So there are two y's here. The first y is the parameter, is a coordinate of the data point yi. And then the corresponding values of y on this curve when x equals to xi is this. If you compare the values of y and yi, then this is called the delta I. So the delta I here refers to what we call the discrepancy. Okay, the discrepancy between the values on the model, which is y, which is f, evaluated fi, and the values of the coordinate of yi. So this yi is from the data point. So this is what we call a discrepancy, and sometimes you call it and sometimes you just call it the residue. So each point, the difference between the data point y and the values on the model continuous function y equals to f is what we call a residue. There are many residues. Some of this residue. So the residue square represents the total area between the functions that you want to fit and the data point y. Right? So if you can find the best value for parameter, then you expect that the sum of the residue square would be the minimum. So in that sense, you'll be able to get the best fit curve that goes through all data point as much as possible. Okay. So what we need to do in order to find out the best value that goes through the data point, you have to first construct residues functions. There's function in the Python that will allows you to find the best value for p such that the is minimized. So this is the idea behind the optimization problem. So later on, we are going to use this function, which is called least square. Right? So least square is a function that is provided by SciSpy that allows you to do this model fitting. So this is a very general class that you will often see in your experiment. Right? So the experiment, you get many data points. Then you want to fit your data point against some model. And in your model, you have a few parameters. So how do you adjust this parameter to obtain the best fit? So you use the least square functions. And then in order to use the least square functions, you have to follow the syntax. Okay, so later on, we'll try to learn how to use the least square to solve a given problem. So in a given problem, usually you are given all the data points. So in this case, your xi, yi. Then you have to define your parameters in the square functions. Then you have to also just follow these instructions. Then you'll be able to find it. So we go to this in a minute. So for the moment, get any response from you? Any questions? I can't see you since most of you do on your video cam. So just pause for a while in case there's any feedback from me. Okay, so no one is saying anything. If you want to say anything, you just talk to me through the chat. So I hope that at this point of time, you understand. Okay, fine, Benny. So at this point of time, you should understand what we're going to learn today. So these 2 hours, we're going to learn only one function called the least square method. Okay? It's a very important method and it's very useful. So once you learn how to use this least square method, next time I give you any data point and I'll give you any model, then you should be able to fit for me the tutorials for you yet. I'm going to do it tonight after the end of this lecture, where I'm going to give you a functions with few parameters. I'm going to give you a set of data point. Then you're going to find me what the best fit parameters. Okay. So in order to do that, you have to learn how to use the syntax. But the syntax is a bit not so straightforward. In Mathematica, we also have this model fitting functions, which is very easy to use. But in Python, the functions model fitting is slightly complicated. So I have to be very careful to teach you how to code and use this least square method. Okay. But before we really use least square method, first I want to do some exercises. Fine. So before we can start on, let us try to do some exercise. Let us try to generate a mock data. So in this exercise, we need the of data point x and y, xi, yi. Now, of course, this xi, yi can be easily found from anywhere you like. But let us try to generate a data point that looks like a sinusoidal function. But at the same time, also, it has some fuzziness in it. So, mic is on, so I have to switch off the mic. Okay, Nolly, Okay, any Nolly is there? Switch off the mic for Nolly. No? Switch off the mic. So let's continue. So what we're going to do now is to try to learn how to generate a set of a random data point. Now, we're going to learn a very important syntax today that is called random. That is, you can easily use a random function to generate the a value, random values. So let's see what I'm going to do. Okay, so this is basically the code that I am writing. I've written this for myself, which is slightly different than the Toronto University website one. So if you run this, you see this. Okay, so what we want to do is that, first of all, we define the sinusoidal function, right? So we define the sinusoidal function, then we want to generate a random data point which are sort of like centered around the well-defined sinusoidal function. So we define this sinusoidal function first, then we plot this red color dotted line. And this is called a template. So I have to first specify the values of A, the period, and theta. See, in the sinusoidal function that you look at this, the sinusoidal function is learn in your Form 5. A sinusoidal function comprised of 3 parameters. A is amplitude, T is the period, and theta here is the phase of a sinusoidal function. Right? So a sinusoidal function has 3 quantity. So you just have to specify what is A, what is T, and what is theta. Once it's specified, then you can plot the function. So A sine 2 pi theta plus x. So our purpose is to generate a mock data, right? A template, okay, a mock data where the xi and yi do not follow exactly with this function, but slightly deviate from it, right? So what you do is that first we're going to generate these template functions. Then for each of the x and y point on the template function, we're going to shift x and y. We're going to shift the values of x and y slightly. Okay, slightly. Then we're going to collect data point into a x data and y data. So our purpose is to generate 2 sets of x data and y data, which are representing this sort of random mock data, so that we can then use this x data and y data to perform a model fitting. Now, the reason why you want to do that is because if you generate the data yourself, then you know what are the basic functions, right? So if you use, say, for example, A equals to 1, T equals to 1.3, and theta equals to, say, 45 degrees, then you know what is the exact the exact function from which the data point is generated from. So later on, when you perform a model fitting based on the random, based on this data point, then the result that you got should be more or less agree with the original functions. Okay, maybe I'll show you finally what we want to get here. So this is a function that I wrote. We are going to come to this part later on, maybe at the end of this lecture. Now, these are the blue dots are the template data point we're going to generate model fitting. This is the fitted data using the least square method. So the least square method that I use to fit the data give me a number, a result. So this is the result that I obtained. I think this is the result that I obtained from the least square function. So this is the result that I obtained based on the data point. And what is the exact values for the A, T, and theta? So they are given by this. So this is number A naught, theta naught, A naught, theta naught, and T naught is the values that I use to generate the original functions. And these are the results obtained in this square function. Okay, so these two should be comparable to each other if my function is, if the parameter that I found is correct. So I hope that you understand the idea. Okay, I'm going to generate a set of mock data, and then we're going to use this as as our example to obtain the best fit parameters. The best fit parameters that I obtain later on should agree with the original template function that I begin with. So that's how I do it. Okay, first of all, I would generate the mock data. So the way how I do generate the mock data is like this. So I specify the values of the amplitude T and theta naught. Right? So I start off with this number. So I decide that my A naught should be 0.75. The period should be 3.7, and then the theta naught should be 1.3 times 45 degrees. Right? So it's pi over 45 degrees. So I'll just simply choose some random number. So I'm going to use this random number to generate my template data. So it's very easy, right? So I generate this data, this line template. So this is done by using this y. This is the one. This is called y template. The y template is a function that I define based on the values of a t naught, theta naught. Right. So this one template. So when I plot the y, I slotting in the argument a naught into a, t naught into t, and theta naught into theta, then I'll obtain this function, and this is to be so the function, that's the part that gives rise to the dotted red color. Okay, now I'm going to show you how you can obtain this data dot based on the red color function. Right? So this is basically the function of y limited. Function of y limited is very simple. Is that in order to generate every values of y on the for data point, instead of the values of the function based on this, I'm going to make the values of a little bit fuzzy, and I'm going to make the values of t a little bit fuzzy, and make a little bit fuzzy means that the values of theta and t and also a that is used to generate the data would be slightly different from a naught, a theta, and theta. Okay? So you see, this is AR. AR is a number which is a multiplication to the original values of a naught. So this is a naught. This number. What is this number? This is a number of 1 plus some random number, which is some random number that lies between 0 and 1. So I'm going to use this np.random.normal with a bracket to generate a number which is lying between 0 to 1.0. And this number will be multiplied by some slightly small number, which is 0.1. So therefore, this code that you see on your screen, AR equals to 0.1 random normal plus is 1 plus some small number. So that this number, when it's multiplied to A naught, then it will make A naught to be slightly different from original A naught. Now, you can multiply the same factor, well, not the same factor. The perturbation, what you call it, the perturbation, the one is, so if this random number is 0, then theta r will be the same as theta naught, right? So if you make this number to be slightly larger than 0 but much less than 1, then this one we call a perturbation. So you introduce a perturbation, which is number less than 1 to 1, you multiply the whole thing to the original theta. Then you would render the theta r to become slightly different than theta naught. For example, if theta naught here is say 45 degrees, then this theta would be about 45 degrees plus minus 0. So is the theta r. Right? So the theta r is defined based on theta naught, and then this theta naught is to be multiplied with 1 plus the perturbation term. Now then, when you do that, AR, theta r, and TR will become a number which is slightly different from A naught, theta r. Then using these numbers of AR, theta r, and theta and TR, then you can use it to calculate the values y, where you fit in the values of AR, amplitude, period, and theta r to the function of y template, right? So in this case, the y template values of A will be replaced by AR, t will be replaced by theta, and t will be replaced by tr, and theta r will be replaced by tr. So by doing this, you'll be able to generate the values of y, which is slightly different from the y. So this is how I use to generate this data point. Okay. Maybe you want me to show you how to generate this again from scratch. So maybe I do that. If you are okay with me. I think some of you who understands the idea can do the programming. Maybe some of you cannot follow what I say. Spend not too long to generate this original data and then also the data. Let's try to do it. So let me open a new panel. Then there's this. So I need this input and basically the thing. So I random. So is a random from numpy. So you can try help HELP. So this random help has very simple function that looks like this. Random give you the random give you a number which is lying between 0 and 1. 1 is not included. Right? So let's try if you can get anything from it. Print random. So you get a number. Random things like this will give a number that's lying between 0 and 1. So if you press again, you get another random number. You press again, you get a random number, which is differently. So this is a introduce some kind of fuzziness into the program. Okay. Now, I define function of y. So this function is called y template. I'm going to use to generate the sign function. So it is going to be the x coordinate and also in the phase displacement. So I'll just call this well, A with sine. We have 2 and then we code this function into the definition and then we're going to print it out later. So it's going to be 2 times multiply with x like 2 pi x over 2 pi x over t. 2 pi x over t, but t is and I'm going to define amplitude for this A0, which is 1.0. This 1.0. And then maybe t is also say 1.0. I'll call it t0. I'll call it 0 equals to say 45 degree. 45 degree is MP pi over 4. So this is 45 degree. Okay. So just make it 1.0 times it. So this is 45 degree. So I have defined my function y template. So let me now try to also generate my x data. Okay, x data is a number that should span from x1 to x2, where x1 is the lower limit, x2 is the higher limit. So you can use this arrange. Let's see if I use in space. Maybe let us try this. NP arrange is going from say 0 to say 2 pi. Okay, 2 times n dot pi. And then you want it to be say separated by say 0.1 times say I over 2, I over 4, for example. So you can do that. So you start off with 0 and then you end it at 2 pi, and then this is as intervals. Then you can print it out and see what happens. Okay, what's the problem with that? NP has no attribute as NP. What's the problem? Sine 2 pi NP arrangement. Again, I always make this stupid mistake. ARRANG. So print out this number called X data. Okay, so this is how you can have X coordinate from 0 to 2 pi. Well, this is roughly 2 pi, but not exactly 2 pi. And then you specify the intervals. Okay. Now there is another way to generate a list of number. So for example, in this case, you specify, well, in this case, you specify the beginning and the end, and then you specify the intervals. Now sometimes you just know, well, the other way to do this is that say you say equals to say 25, for example, 25, then the delta, well, delta theta is just the last number, say x last. Okay, so here x last is say 2 times dot pi. So that you specify this x last number, and then the delta theta is s last divided by np. Right? So by doing that, you can generate X data to be in this form. So you say, okay, what is the numbers of intervals that you want? What's the last values of your X data? And then this delta theta is defined intervals in the X data you use to generate it. How does it looks like it? X data NP, X data X last to be this. Delta theta to be x last with the np x theta x point 0 0 x last. You know what happened, but it shouldn't be like that. X0 to x last in x data. So I'm expecting a not this. I'm expecting say what is this? Say x last. Okay, so should be this number, and then delta theta. Theta should be like this. So a range should be from 0, x last, and then, okay, so this is not NP, this should be delta theta. Okay, so with 0, x last, and this is the subintervals of x. So that is how you obtain the set of x data. Now, sometimes this is a bit not very convenient. You can actually have a better way or no easier way, which is called lean space. A lean space is one is being taught to you, so we need to use this space instead of NP arrange. So it's very easy. So instead of using this, what you do is that you say NP space linear. Well, linear space here basically refers to linear space. So the linear space, say, start out with something, initial value, last value, and then you just simply say how many data points. In this case, you say 20. So in that case, you do not need to define your interval, You just have to say NP, how many intervals you want to have between the last value and the first value in the linear space. So by doing that, you're also able to generate a list of numbers. So this NP is 25. So you can count here 1, 2, 3, 4, 5, 6. So if you count it, this X data should then contain 25. So if you want to say 50, then you just make 50 intervals within the linear space. So that is another simple way to generate a list of X data beginning from 0 to X last. Okay, so that's how we do it. So now I have this X last and X data. So now I'm ready to plot. Right, the plot is, remember, is to X data and Y data. Now what is this Y data? This Y data is the values of Y that Okay, Y template, Y where the values of X is in X. So in order to generate this Y template data, let me show you first how you do that. I think I've done this before, but I don't mind doing it again. So in order to plot the functions, so we need to first define all the points, and then we also need to sort of like generate all the values of Y in the X data. So how do you do that? It's very quite simple. So you say, I want to generate the value of X template where A is A0, T is T0, theta is theta0. By doing this, you are calculating the values of Y template. So just show you this. Okay, so if you say X is equal to say 0, then you can print the data with a number. So this number is the number that is calculated from this. Okay, so the values of the function Y template at X equals to 0, where A naught, T naught, theta naught is defined to be like this. Okay. So if you change the AX to be some becomes 0.1, you got another number. It changes to be, say, well, maybe 5 or 2, you get another number. Okay. So now we can use this template to generate whole set of array. So let's to make X to be variable. Is a variable in X data, right? So by doing this, I'm going to generate a whole array where value be evaluated for all X in X data. So as a result, what you get is a list of list of X. This is like this. I think we are going to generate an array of Y template for X in X data. This is going to generate for me an array of Y value. Okay, so this is an array of Y value corresponds to each values in the X data. So I have this Y data. This is the Y data. So if I were to plot my X data and Y data, then that is what I'm going to see. Okay, so that's how you do the plot. So, well, maybe I don't call this Y data, just cut and paste this. And I can just paste this thing here. And then I'm going to plot this. Maybe a red line. So this is what I see here. Okay. So this is the template data. And you can actually make this template data to be finer by choosing make it 100. Then this for the function y equals to a sine 2 pi x o t plus theta. So you can make this any number you want. Make this okay 0.3. You can make this say 3.13, and you can make this to be say 0.73 whatever. Then in that case, you change. Then the functions that you get is slightly different. So that is the first thing. The next thing is that we want to generate values of y which slightly deviate from the y value. So in that case, I have to define another. In this case, I just call this y. What do you call the name? I call y simulated. Okay, so simulated. So for y simulated, we are going to read in A0. Well, read in A0, read in theta, and read in theta. No, well, there are many ways how I do it. So let me see how I'm going to do this. Y simulated. Okay, never mind. Just leave it like that. Now, so in my case here, the values of A that is going to be generated should not be the A. It will be generated using the A is slightly different from A. is going to be AR times A naught multiplied with 1 plus perturbation. Okay, so what is a perturbation? Perturbation is a random number, right? Slightly random number. Now this random number will be a number which is 0 to 0 to 1.0, so it could be like 0.025 or 0.002. But and if you compare this number to 1, then this random could be very large. So you want to make this slightly larger, then you multiply by 2.1, so that you make sure that the random number generated multiplied with 0.1 is slightly well, it's much smaller than 1, so that could be treated as an perturbation. Right. So instead of calculating the values of A at A0, we calculate AR. Now, likewise, you can define T to be a TR, and this is going to be T naught. So this is going to be your TR, and again, we're going to define theta R to be just a theta 0. Okay. So so this is a theta 0. Theta 0, theta, maybe I'll just call this let's just call this that should be not the case. Let's call theta, T and T. So in order to calculate my similarity, what I need to do is just I have to generate this number. I'm going to plot x data. I'm going to generate the simulated, where I'm going to slot in A with A naught, T with T naught, and then theta with theta. So this set of number should goes into the Y simulated, so that when A naught is passed to A, and A that comes to here will become A0. Then AR will be calculated based on A0 in Y simulated. So is TR and theta R. We are late. So by doing that, I'm going to have Y simulated, and I'm going to plot it with a dot, maybe a dot, just I think it's a 0. Oh. So that would allow me to generate two plots. One is a plot data which is simulated, and the other one is the one that is the template data. So that's how I do it, right? So all the values of Y is slightly shifted from the template by a little bit. So what I have done here is that I have then successfully generated my simulated data. So I'm going to keep this simulated data. Y data to be just this set of simulated data. So I'm going to define it here, and then I'll just call this Y data. So this Y data is the data set that is perturbed, whereas this is the one that is original. Okay, so if you compare the perturbed data, then you realize that this perturbed data is basically generated from the values of the Y template. Right? So the Y template is generated with values of x of A, T, and theta. So you can control this quite easily. Okay, so let me check if there is any problem. Random. So it looks to me is correct. So I just perturb the theta, random number. See, it looks like the perturbation is slightly on the right hand side. So I'm not sure what has happened. It doesn't look like it's that's what I expect. Perturb A, not theta naught. I think it should be okay. A, T, and theta should be just perturbed. Okay, so this should be AR sine pi 2 pi x TR and theta r. So my y data for I. So let me try to calculate again. Start and clear all out. And run it again. Where am I? This is the one I just written. Okay, so it looks like this is just the raw data. It doesn't look as what I expect because it looks like the data is sort of like biased. It's not like I expect to be like distributed above and below the template, but it looks like it is not. At least I have performed some perturbation to this, and I have done that. Okay. So at this point, I have got my perturbed data, which is, so let me plot it here. This is my perturbed data. So this is the perturbed data, which is basically the same data I shown you in the beginning. So this is how I generate my my perturbed data, so that we can use it to the next problem, right? So the next problem is to do the fitting. So this is going to be like this. We are going to find out what is the best values of E, theta, and A that would do these simulated data. And the result is already known, right? We know what is A, what is E, and what is theta because we fix it in the beginning, right? So I fix like this number, and this number. So later on when I fix it, I the optimized parameter near this number. Okay. So that is the first part of our lecture. But before we take a break, I'll just give you some review what we're going to see. We are going to say fit the x data, y data using fsolve. So fsolve is a function that we have seen before. And suppose you have also learned how to use fsolve to submit your assignment, right? So you can ask to fit the model, right? So if you fit the model, you find out that I think I tried it many times, but that is obtained from the find fit does not do a good job. It gives this sort of problem. If a problem is doesn't fit very well. So this is what we are going to do. They use form the fsolve to do the fitting, and then we're going to show that this doesn't do a good job. The find fit doesn't do a good job. So we're going to use this new function to do the fitting. So that will be the second part of today's lecture. So it's 401 now. I think you could be too far lecture. So maybe take a break. Minutes. Okay, so today is slightly longer. So I'll come back here at 408. So at 408, we will come back to this lecture. Okay. Any questions before we take a break? Any response to all? No? 408. Okay, so people, are you still there? I see there are 28 participants at the moment. Some have, but I hope they come back later. So, okay, so to continue our lecture. Now, any questions you should ask me on the chat, or you should also switch on your. You can switch on your mic, then you can talk to me. I'll stop when I hear sound from you. I'll just pause to respond to your questions. If you're too quiet, then I will proceed with my lecture. Okay. Okay. So let us go back to the five. One, two. lecture notes. Here's my lecture notes. So let me see. Lecture 5 is appearing. Now, just to recall, lecture 5, when we talk about the form fit, the five fit. So the five fit is a very important function as well in the in Python. So remember that in the previous functions, have let me recall where it is. Okay, so this is an example. Now this is an example that I called out from the part 5 of our lecture about a year ago. So in this example, you have the X data, you have the Y data. I'm showing it on the screen. I can just switch off this one. Minimize it so I can maximize the panel. Okay. So you get your 5 of the lecture. This was what we did, right? So you're given the X data. No, this one. You're given the X data and Y data, a set of data points. And then you have a function, and this function is called ax squared plus bx plus c. And then you have these three parameters, a, b, and c, which you try to find. So to do that, you use a sciSPy optimized curve fit. And then you tell the curve fit what is your function to fit. And then you provide the x data and y data. So this x, the values of x, and ABC are the three parameters that you try to find. So in this particular example, the data point seems to be very nicely arranged so that when you press the button, you are able to find out what is the ax squared plus bx plus c, what is the values of ABC. So in this particular case, it works. So I just want to bring your attention that you can, in principle, solve this model fitting problem using F to fit, right? As long as you have X data, Y data, then you can call the curve fit to do the optimization problem for you. So let us try to do it here. Okay, let us try to do it here. So before we start using this method, let us try to use this method called the find to fit. Okay, so let me try to do it here. So you can try to read it for yourself. But let me recall what this is. The X data is a set of array that is like this. And then Y data is this set of array, right, which is already calculated. So X data and Y data is displayed and they look like this. Let's try to fit the X and Y data using the sciSPy optimized. Right? So we're going to use this science optimized curve fit to fit our data. X data and Y data are already in the memory of the functions. So I just need to define F to fit. I just have to define this F to fit. Then X is the variable that should go into the function. A, B, C have to be defined. So this is my A, this is my T, and this is my theta. So the function that should be defined for F to fit should be a function which is like this. It should be like this. I just cut and paste. So I'm going to generate this function to be A sine T and B, which is like this. Okay, so these two lines would define the function to fit, and then it should goes in, it should bring in X. And then you try to find me the best value for T and theta. So let's see what it get me. So when I press the button, I get some number. Okay, I should get some number. So this is the number that I obtained. So according to the questions, this is the parameter A, the parameter for T, and this should be the parameter for theta. So, but then you still remember this. a 3x3 array, which tells the error in the parameter found. This is the error in A. This is the error in T, and this is the error in theta. Okay, and this is the answer in it. So it looks like it doesn't look very good. You know why is that so? Because in this error functions, right, the diagonal is the values. Okay, so this is the values of 13, right? And the values for the theta that's found is 0.297. So theta is a small number, but the error is a very large number. So it doesn't look very good. Okay, because the error is usually should be much smaller than the values of self. Okay, so anyway, let me put out the zeroth component in the error. So this is the values of the print results. The A, what I call it fit, using the F-solve, I just call it AF. Okay, this is the result of the best parameter A from the best fit. So I call this from the method of curve fitting. So I'm not F-solve. I'm confused. Okay, so I'm talking about fitting the parameter, the model using curve fit. So it should not be F. So here I said is F-solve. Maybe I was wrong. Okay, so we are going to solve this problem using not F-solve. So this should not be F-solve. It should be perfect. So it's perfect. Not F-solve. This is called perfect. Curve fit. Yeah, I'm going to make the corrections later. So then this is curve fit method. So I'm going to define my A based on the curve fit to be just the first component in the results, and then the T is the best fit parameter is obtained from curve fit, which is the second component. Okay. And then it should be then theta curve fit, which is the component. Okay, so to print out ACF, TCF, theta, CF. Okay, so these three numbers is exactly the same thing. So these are the three numbers for best fit parameter that's obtained from curve fit. So we are going to plot these functions. We will plot these functions F to fit using the best fit parameter and then display it. So what I want to do now is to print out the curve using the best fit parameters and then compare it with the data. So the data looks like this. Like, look, the data looks like X data, Y. So it looks like, but maybe I should just call this a dot. So this is a dot data. For that, I'm going to plot the X data, and then I'm going to the Y coordinate obtained from F to fit. Right. So this is going to use ACF as is input, TCF and theta CF. And then this is going to generate for X in X data. So this should give me a plot of the fitted function using the parameters obtained from this method called size optimized curve fit. So when I plot the data, both I should see two lines and also the dotted line. Right. So what I'm saying here is that this is the functions of the values that from the curve fit, and the tell me that the A is this number, and then this is the T, and this is the period. Whereas the correct number, okay, should be A0, T0 and then theta 0. This theta naught. So this should be the correct number when you compare to the found one. Right? So this is what is given from the 5 feet, and this is the correct number. So you see there's a lot of difference, right? The period is up totally, right? So the period is 0.5, and then the time, so the period is totally up. It should be 3.14, but here it is this is different. Okay, so theta naught, yeah, theta naught, A naught is actually theta T0 is 3.14, but I got this number. So what I'm trying to say is that if I use this method, then the parameter that I obtain is not fit, and then you compare the data with the fit function, and this is what it looks like. Now, I want to comment another thing about using this curve fit. And this curve fit, everything is fixed, right? So you have no random number in it. You just have the x data, y data given to you. This is the function you want to fit. And this is the A, T, and theta you want it to find. So you say, find me the best value. Then just try to find it. And then what you got is that it's the wrong answer, right? But if you use a different method, which we call, so this is, should be, there's no need to call fsolve. Fsolve in this case. What is the curve fit? So basically, this is just what I wrote here. Exactly the same thing. Now, let's just move on. Let us solve the same problem using this square method. To solve this problem using this square method, the syntax is slightly different. Okay. So in order to obtain the best fit parameter, which is what we want here, we have to use the definition for residue. So we have to define the residue. So this is the syntax. Okay, the syntax of the least square function looks like this. You have to provide a guess to the parameter you want to find, and then you have to provide, of course, the x data and y data into the least square function, and then you have to define your residue. Allow me to say that now what you want to find is the best fit parameter P. So there are 3 parameters: A, amplitude, and also the phase theta. Right? So and then you know what is the function looks like. The function is A sine 2 pi x over t plus theta. And then you know what is your free parameter there. And then so you need to provide all this information, right? You have to define your theta, the residue, how the Python, what is your x data and y data. This is x data, and what is your function to fit, and then what is your parameter. So you have to do this one by one. So the data, and then also the form of the residue. The residue should contain the form of the function f, right? So you have in the residue, what is your function, and you have to provide initial guess. Now, this is a different. This is a part that is different from the from this method, the curve fit. From the curve fit, you do not provide initial guess, right? So just say, tell me what answer you find and give me the answer. But in the method of residue, you have to provide initial guess. So initial guess is very close to the a very nice fit. But if the initial guess of the 3 parameters off too much from exact value, then you will not get anything. Okay? So let us try to do this. So the answer is here, but let me try to reproduce the code all by itself from scratch. So so what I need to do is that I need to define my residue function. So what is my residue function? The residue function is this, like the difference between yi and f evaluated, and then you have to define your parameter. So before I can define the residue function, I have to define function to fit my f model. So I'm going to tell my what we call f model. So this f model is a function that should contain function I want to fit. So this function I have a, and I have sine 2 pi times x over t, and then also plus theta. Okay, this is the function I want to fit. Return. Now, when I do that, I am supplying this with the variable x, right? But then I have to also define my parameters. So when you define your residue function, your function to fit f should also the parameter supply or tell the Python what are your parameters and how many of them. So there are 3 of them, p. So the p should comprise of a, comprise of t, and comprise of theta. Right? So these 3 are the parameters that should goes into the function. Your MATLAB model have to supply with the parameter. So let me call this P. And what is this P? This P should be the values that goes into A, T, and theta. Okay, so I call this. Now, what is the value of A? A is a number that should be the 0th component of the parameter P. So we use this P to represents an array that contains the 3 parameters, whereas the values of t that is in the F model is the values of t to be evaluated based on p, and then theta is the values of the at 2. Okay, so that is how you define your F model. So you define your F model based on your p parameter as well as x. Okay. Then let us try to define my residue function. Residue functions is defined. Define my functions. Define my residue. Now the residue will take in some variables which I'm going to define later. Now, what is your residue? The residue is the difference between y minus the function of f model. I think that is what you write. So this is the residue function. It will have written x, p, and also y. So the residue should contain a variable of p, and x, and y. Right. So this p has to be supplied. X has to be supplied. X is the x data. Then when the x and y and p are supplied to the residue functions, then the residue function return the values of the difference between the y coordinate and the functions of the model evaluated at p and x. So that is how we define it. Then what you need is just to say this, let this square x data, y data. Now in this case, you have to first define what is your p. Now this is a p stand for the parameter initial guess. So the parameter initial guess should be 3 numbers. So this should be the first number that would be representing the values of p, and the p comprised of 3 components, p0, p1, and p2. So the first value that goes into here should be your initial guess of a. And we do not know what is the exact values of a at this moment. We just pretend that we do not know what is a. So just put 1, 1, and 1. Just simply put in 3 initial guess. Represents the initial guess for the 3 parameters we want to find. And this is your residual functions. And then this is your pi, and this is your argument. The argument should be the x data and y data. Now, I'm not sure whether this is the correct way to do it, but let's just try to print out the answer to see whether it works. Is squared. Now, maybe there could be some error. I'm not sure. I'm not very familiar with this, but let's try anyway. So the residual function will be like this. It's not correct because this square is not, because I have not import size by import size p. Sorry, size p. I have to import this. Sorry, from size. In order to use the least square function, I have to import size pi in my. So residual is not defined, I think, because I have an S here. Residual has an S. Okay, that's a number, but it doesn't give me an answer. That is correct. So let's see what is it. Okay, so X argument P, F model P argument. Okay, so when I define my residue, I have to be very careful. Let's see what's the problem. The function is properly defined. F model contain P and X. So this is my F model P and X. P and X is defined here. Did you have to P as a parameter? Okay, sorry. I think I have done it incorrectly. Well, maybe it's correct though. So in my residue function, I define my P, and then I define my X and Y argument. So this is a Y argument. What goes into this argument is Y, and this should goes into is so it looks like it's, I don't get my answer done. So let me execute this anyway. So if I got it right, okay, should put NP sign. Yeah, thank you very much. I'm very happy that people are responding to me. So I have an error here. This should be sign which is not running. So I forgot this NP. Yeah, no, yes, no, no. Even though I put in this NP, I still got some problem. But anyway, let's try to print out the values of the function. Now to get me correct, when I print out the residues of P, P should be initial G, and then X is some number, say 1 and 1, I should get a number. Right? So I'm doing some troubleshooting to see whether my function is defined properly. So I get this number which is defined properly. F model. So F model should also be correct. So it looks like there is no answer. So I think the code is correct. Let me print out the residual. Let me call this a result. So I print out. Yeah, correct. So the result is that this is the residue. Sorry, this is okay, so it looks like I have got some answer. I make a guess of R, this function. So I guess the initial values of the A, T, and theta to be all 1, 1, 1. Then the initial guess to the function of residue. And then I provide the X data and Y data. So it looks like I have obtained my answer. So now I'm going to check my answer if this is correct. So same thing here. I'm going to plot my data. And then I'm going to see whether the data that is obtained from here is indeed the correct data. Okay, so F fit will be this number. And then T best is the number that is obtained from the list. Okay, so I'm going to plot this. I'm going to plot the X data, Y data along with the function. And so the function is F model. I'm going to got my model here. This is model, F2 model. The F2 model is defined in terms of P, X. Okay, so P here should be, this should be the P and X. Now Now this is the values of obtained from the above. A best is this number, T best result, and T theta best is also the result that's obtained from the least square. So these three numbers will go into the F model, A best, T best, theta best, for all x, where x is in x data. Right? So this is the definition of the F model. This is my F model. So my F model has an array P, which is comprised of three numbers. So this three number is a P. Let's see what I get. No, something is F model, three position, blah, blah, blah. Okay, fine. So it doesn't allow me to find my F function to be like this. So I have to this up, and I call this P best. Okay? The P best defined to be an array comprised of these three numbers. Okay, so I in one variables, which is P best, and this variable P best represent array numbers. So let's see again. Yes. So this is my result. It doesn't look good, isn't it? It looks like it is not the correct way. If I get the correct data, then if I got the correct, then I should see it goes through all these data points. But no, it doesn't look like. Now, why is it so? Because I am starting it with a number, which is 0. No, I'm using the initial guess, which is 111. So seems to be not good, and it doesn't give me the best. So I need to try another initial guess, maybe 5. Well, when I change 5, then it gives me the correct answer. Okay. Something else, I might get a different answer. So my initial guess should be say this is 5 and this is 5. I get it doesn't got me correct number. So sometimes if you are lucky and if your data are not too much off from your model, if your data and your function are not too much different, so when you define your initial guess, you could sometimes quite easily can obtain the data. So there are 3 parameters you have to guess. So you have to keep on trying until you get the best number. So it doesn't go. Sometimes if you are lucky, it gives you the correct number. Maybe it isn't correct, right? So sometimes to make a guess for 3 different parameters could be very much dependent on your luck, right? So just now I got it right. I got 1, I think 5, and then this is 1. Now what happens if you do not get it right? So what you do is you can actually try with the random. Okay? You can do a random number, and then you do a random number. So you let the random number to decide on your initial guess. And if you want your random number to be not restricted to say 0 to 1, you can multiply it with some integer. Multiply by 3, by 3, multiply by 3, so that you got a number which is slightly larger than 1. Right? Because random number here only range from 0 to 5. If you want, you can actually make it to be called negative as well. So you have to think of your way to generate random number, which could have also negative number. In this case, the random number only gives you positive values from 0 to 1. So if you want to generate a random number, say from -1 to 1, and then you have all these values of -1 and 1 in between, then you have to figure out how to do it. Actually, it's quite easy, right? Okay, so if you want to have a random number that is ranging from -1 to 1, you just have to think of yourself. It's very easy. I think you can figure out yourself. So now I am allowing the random number to define for me initial guess. So I just give it a try. The first try doesn't give me the correct guess. So the correct guess is some number which is different, and it gives me a different number. It gives me a wrong number. So if I try it again, then the new random number, a new set of 3 random number would generate. It doesn't look good. Again, let me try again. It doesn't look good. Try again. There will be some time when the random number hits the right value. when the random number hits the right value, which is very close to a solution, then the optimization problem will drive you towards the correct answer. Right? So instead of manually put in the initial guess, you can try to use a random number generator or random number to generate this your initial guess. Okay. At this stage, is there any questions from anyone? Now, I just give a test since we still have some time. Now, if you use random, you generate a number which is between 0 and 1. So I'm trying to ask if you can, how would you generate a random number which is lying between minus 1? It's very easy, okay? So make a mapping. How do you make a mapping? Let's see if I can do this one here. I try to use a white. Okay, you can see me. Yeah, I'm trying to use this. So let's say you have a let's say you have a function that looks like this. Say this is x, which is a random number. Random number starts from 0 to 1, right? So if you throw a random number, you always end at some number which is known between 0 and 1. But if you want to generate a random number which is lying between minus 1 and 1, imagine that this is the y-axis, this is the y-axis, this is y equals to plus 1, and this is y equals to minus 1. So what you want is that you want to generate a random number that is between, well, x is between 0 and 1. Right? So if somehow you can draw a line from here to here, right? So that you, for every values of x that is generated, you can find a corresponding values of y. So if you generate a x here, then this is the corresponding values of y. And if your x is, say, generated to be here, then the corresponding values of y would be here. Right? So that allows you to well, for every values of x, then you can map it to a values of y. And if your x is from 0 to 1, all the values of y that lies on this straight line should then be lying between minus 1 to 1, right? So what you need is just to find out what is the function for this y in terms of x, right? So y is what? In this case, y is to mx plus c. So mx plus c is, this is 1, this is minus 1, this is 0.5. So you have to figure out what is the slope. So this is 1x, and then this should cut through the values of minus 1. So y goes to minus 1, I think. Yeah. So no, is it correct? So when x is equal to 0, then y is minus 1. When x equals to 1, the value of y is 1. Okay. So by generating the value for every x, you get a y which is lying between minus 1 and 1. Okay, so this is the formula you want, right? So for every x, call this say x random, then you call y random. So y random is just x random minus 1, isn't it? So based on what I shown here, the formula is y equals to x minus 1. So it will be xr random minus 1. Okay, then you can print out xr and yr, and then you just try. So then you see your y is this number. Okay, you try again, then you got another y. Try again, you got another y. Try again, you got another y. But it's not quite right, isn't it? Because in that case, your y is always negative. So I think my function is not correct here. So I just have to figure out more correctly what is this function looks like. y equals to mx plus c. So this is not a correct function. But the idea here is same, right? So x lying between 0 and 1. When x equals to 1, y equals to 1. When x equals to 0, y equals to minus 1. So what is this function? This function is mx plus c. So the m is the slope. The slope is this. This is 2. This is 2 and this is 1. So that should be a factor of 2. Okay, so not x. So that's a factor of 2x minus 1. So I come back to here. 2x minus 1 instead of x minus. That should be in this case. See, now you have x, which is lying between 0 and 1, but the y is between 0 and plus. So now you see x, this is y. Right? So if you keep on trying, you'll be able to generate the values of y, where this y is always lying between minus 1 and 1. Okay? So maybe I can do a better job by saying this. So this is my random. Say for I in say 100 of them. I'm going to do this and I'm going to print out the values of yr. Then you see what is this? Random for I in 100. So this is range of 200. So I'm plotting 100 values. So you see that these are all the values of y, which is always lying between minus 1 and 1. Right? So that is the idea of using random number. So in the next lecture, which we will see next week, probably we are going to look at the statistics problem, where we are going to generate using random number, different statistical sample using this method as well. So we're going to use a lot of random number, and then we're going to generate a lot of data, and then we're going to try to sample the data to calculate, say, the average of this data, the mean of the data, deviation of data, and things like that. So this is basically today's lecture on using the least square method to perform a model fitting to some complicated data. So based on this idea, you have to use this least square method to find the best fit parameter for the set of data, and then you also have to define your residue. But basically, this program is good enough. You just have to know how to modify your model. Anytime if I give you a set of data and then give you the model to fit, you just have to make use of this. You can fit every model onto any data, even though the data are sort of like complicated. If it's a straight line, then it's quite easy. If the data is a straight line data, you can always use a line fit or the curve fit. But for the least square method, then it could be used for many complicated data. So, you're going to perform the exercise based on the assignment that I'm going to give you maybe tonight or tomorrow night. So be prepared for the lecture next week. We're going to talk on the statistics. Okay? Now, before we leave, I actually have no feedback from you. Any one of you who have friends or have any person in your class that do not have the computer access, please let contact me. So I'll think of a way to help you, because we assume that everyone who is accessing this online teaching computer and be able to access the online teaching. I think there are three or four, 2 or 3 students who are constantly missing action. So I don't see them in the attendance sheets. So if you know any of them, could you please ask them to write to me or contact me to see if there's any problem with the computer access. And if any problem, you can contact me anytime through WhatsApp or whatever. So if you have problem with your assignment as well, I'm very happy to help you out. Okay, So it's almost time. So I'll give you one more chance to ask any questions or give me any feedback. Okay. So as usual, most of you do not give me feedback. So I'll let you go off this and be looking out for the assignment to be uploaded and also the recording of this video. Okay. So that's all for today. Thank you for your participation. That's all for today. Okay, you are welcome.